So welcome to part B of the nightmare that is this exercise. Now we will try to show that if uh, we have some point AB that lies outside the set of AB regions for the Poisson binomial and negative binomial distributions, well then that point AB will not define a probability distribution when we plug it into this recurrence relation. And this will play a part in helping us show that uh, a distribution belongs to the AB class of distributions if and only if it is either Poisson binomial or negative binomial. So what we want to do is look at different cases. What happens if AB is here? What happens if A comma B is here? What happens if AB is here? And so on and so on. So let's just start out easy by looking at uh, a, a not too difficult case. So this is A, this is B. Let's consider what happens on the line where B is equal to A, to minus A, or with other words, where A plus B is equal to 0. Now, in this entire exercise, we will have to assume that we will assume that Q0 lies between 0 and 1. And the reason why we do that is because, well, if Q0 is 0, then the recurrence relation just returns 0 for everything. And that's really not interesting because that's not a probability distribution. We can't use it for anything and so on. And on the other hand, if Q0 is 1, then it is just a degenerate probability distribution because then the probability mass is all in 0. So maybe we should show that if does not belong to R, then QK is not a non-degenerate. So with other words, it is not an interesting probability distribution. Okay, what happens if A plus B is equal to 0? If A plus B is equal to 0, then quite clearly we can see that Q1 will be equal to A plus B divided by 1, which is A plus B, multiplied by Q0, and this will just be 0 because A plus B is equal to 0. Then this will imply that Q2 will also be 0 because then we just plug Q1 in here with a 0 and everything will just be 0. And therefore that implies that all the probability mass must be concentrated in 0 and thus Q0 will be 1, but that will imply degenerate. So any A and B lying on this line gives us a degenerate distribution, and we can't use that. So we can now continue on to the next case. In the next case, let's show that we can disregard all A's and B's that lie below this line. So all A's and B's that satisfy that their sum is smaller than 0 because this just means that B is smaller than minus A, and if I pull minus A over here, it means B plus A is smaller than 0. So assume that this is smaller than 0. Well, then using the same logic as earlier, we can see that then Q1 is equal to A plus B multiplied by Q0, and then this thing will be smaller than 0 as well. And that will imply that, well, Q1 is not a point probability because all probabilities have to be between 0 and 1. And that was a nice satisfying feeling because now we've removed this entire chunk down here. So that's a very nice feeling. And the next thing that we can look at now, well, we can kind of choose what we want to look at. we can look at these flimsy things that are between the AB regions for the binomial case. Yeah, let's look at that. So we will consider now, and it's a bit hard to actually describe the set we're going to look at now, but so if we draw the line that's called b equal to minus a, and then we have b equal to minus 2a, minus 3a, and so on. These lines here that are up here, those are the regions of, those are the AB regions for the binomial distribution. And what we want to look at are these things that are between the lines and show that if AB lies inside one of these, then we cannot have that QK defines the point probabilities in a non-degenerate distribution. So what do we write here? Well, let A be smaller than 0 and let B be equal to minus A multiplied by R plus uh, R plus multiplied by minus a multiplied by r, right? Where r has to be greater than 1 and smaller than 2, for example, or greater than 2 and smaller than. So where r lies between um, n and n plus 1, for n lying in the natural numbers. So I'm basically trying to figure out a way to describe these weird sets that are kind of hard to describe, but I think I figured out one now. So this works because if n is equal to 1, then it means that b lies somewhere inside here. If n is equal to 2, b lies somewhere inside here, and so on and so on. So what will then happen? Well, remember the binomial case where what we wanted was that b had to be equal to one of these things, so lie on exactly one of these lines. The reason why the binomial case worked was because from a certain point onward, the probabilities all turned to 0 because the n plus 1 canceled out with the n plus 1 down here, and then I had a minus a was 0. Now, this will not happen if r is not an integer, because then the numbers won't cancel out the correct way. Um, and the specific way we want to break this recurrence relation is by trying to create some point probability that at one point becomes negative. So let's just look at uh, at the sign of a minus a r divided by k. So a plus b over k is a minus ar divided by k. Now this is equal to a multiplied by 1 minus r divided by k. And recall that a is negative, so this entire thing is only positive if this is negative. And let's just, so let's just, how do we do this? So this is only greater than equal to 0 if 1 minus r over k is smaller than equal to 0. Now the thing is that as long as k is sufficiently small, then this will hold. So this holds if uh, 1 is smaller than equal to r over k, and then I can multiply k on this side, right? So if k is smaller than equal to r, and r lies somewhere between n and n plus 1. So what happens if k is equal to n plus 1? So we have established, so for all k smaller than equal to n, qk is positive. And actually, it is strictly positive. It is strictly positive because the because the A is strictly negative. So I should just write without this and without. So it is strictly positive. And there is no point where r divided by k can be equal to 1 because r is not integer. So r cannot be equal to k at any point. So for all k smaller than equal to n, then qk is strictly positive. Well, what does this mean as soon as k is equal to n plus 1? Then qn plus 1 is equal to a multiplied by 1 minus r over k qn. However, now we have that n plus 1 is greater than r. Sorry, that shouldn't be k. N plus 1 is greater than r. And because n plus 1 is greater than r, then this thing will be positive. And this thing here will be negative, and then the entire thing will be strictly smaller than 0. And that's a problem because then qn plus 1 is not a point probability. So which areas have we covered now if we look at these pictures? Well, we've covered this area, we've covered the weird squiggly areas that were kind of tough. So the only thing that we're missing now is actually the area outside here on this strip. So I'll just do a little bit of cleaning up and let's continue in the next video.